No, it actually
Well,
bothers me.
yeah,
If you're sitting in the audience, it actually bothers me.
Oh, really?
Yeah. And your color scheme is good, but if you use like black on white, you can see that things are shifted a little
shadow.
bit. Yeah, and I mean, I figure if we've got a new building and new projectors, you might as well
Well,
have them aligned.
bulbs burn out and, things get replaced anyway. So.
Yeah.
But I like the setup. You can actually see it. Well, very cool.
Yeah, the building is very, very nice, I think. So, pretty good shape.
I'm amazed you guys did it for whatever 20-some million.
Yeah, it's like 28, 29 million.
It looks like a 80, 90 kind of number. Yeah. I mean, I remember Berkeley's Soda Hall was supposedly 50 or something, but
no, it wasn't that much.
Really?
Back in the day, it was in '94 or whatever that we moved in. It was 7 million.
Really? That's that?
Like that. Yeah.
Huh.
That was a lot of money back then.
Yeah.
Alright, so I think we're probably close to the quorum, so I'm just going to do a quick intro.
Yeah, sure.
Okay, everyone, welcome to the CNS lecture series. I'm very excited to introduce Steve and Zhao. I've known Ben for I don't know how long, maybe 14 years.
Has it been that long? Holy cow.
Something like that.
We're
Ben
both old.
Is world famous for his pioneering work on tapestry, which along with cord, can, and pastry really established this area of peer-to-peer research. I haven't checked recently, but he's probably got several thousand, 10,000, I don't know, citations to his work on tapestry, and more recently he's been doing some really exciting work on social networking that he's going to be telling us about today.
Cool. Thanks. Can everybody hear me okay? Yeah. Okay, great. Fantastic audio system. So thanks, for the intro. So today I'm going to be talking about a little bit about some of the work that my group has been working on in the area of social networks. This is sort of a fun area, and in some sense it's a little bit difficult to find the really interesting systems research problems, other than poking around. So, okay, so I'll start at a point where I think a lot of us are familiar with. Security is somewhat of a serious problem in a lot of the online distributed systems today. So whether it's spam in terms of email or it's fraud in terms of online marketplaces, there's a lot of problems that arise from the lack of true authentication or global authentication in the internet. And of course, accountability is a constant issue. So this is also exacerbated by the fact of the decoupling of sort of virtual identities and physical identities, right? So you can do things like Sybil attacks where you can, as many email addresses as you can create, you can create that many virtual identities and have them collaborate together to do nasty things. So there's a lot of approaches to addressing some of these problems. Some are more clean slate designs, and some are more incremental mechanisms. But regardless of what way you look at it, these problems are sort of still around, right? So they're not addressed, and not completely. And there's a lot of email that's still spam. There's a lot of internet fraud based on reports from eBay and other places. So one of the questions that's been asked recently is, can we do something different? Can we bring a new tool to this space? Okay, and in a sense, this is where social networking, at least in some ways, can help. Okay, so the idea that a lot of people have discussed is the fact that social networks may, in fact, embed this natural notion of offline trust between users. And if you can bring that to bear in actual internet applications, perhaps that can actually, improve things, right? Increase reliability, reduce fraud, and hopefully have a positive impact. So just to sort of, push home the point of this, these are some of the bigger social networks that people have known about, right? Obviously, Orchid, Facebook, MySpace, and so on. But what surprised me a little bit was when I looked into this, it turns out there's a lot of these social networks, right? And that, I think, everybody believes in. But what surprised me is that these are at least a sampling of the networks that have more than 10 million users. So this is somewhat surprising. If you look at real substantial populations in different diverse environments. And in fact, some of them are very sort of cliquey, right? So the Where Are You Now is a travel-based social network. There are other ones that are very geographic location-based. There's a Russian one. There's Mixi, which is Japanese. There's Xiaone, which is a Chinese one. There's another one from Poland. And they all have very substantial populations, right? So potentially, if we can get this right, if we can leverage this trust inherent in these kind of communities, there's a lot of places where we can apply this. There's a lot of sort of weight behind this hammer that we can leverage. Okay, so then the question is, okay, what kind of applications can we do? And it turns out that a lot of people have been doing social networking applications for a few years now, right? So I've just listed a few here. There's reliable email from NSDI 06. Essentially, we're going to whitelist email that's been sent from a friend or a friend of a friend. There's Sybilguard, Sybil limit, Sybil resistant voting, things that use social networking graphs to basically detect when someone has been generating Sybil accounts online. Pretty effective. My group did some cute little project last year on how to improve anonymous communication using social networks. Turns out you can protect yourself against passive logging attacks like predecessor attacks. Really nasty attack, really hard to defeat in real internet environments. But it turns out if you put a few of your friends, generate a probabilistic random walk that forms a shield in front of you, you can actually stop these kind of attacks. And it's actually quite nice. So there's a lot of potential uses in some unexpected arenas. And, and then there's a different set of applications, things that are more based on content, right? So if you rely on similarity between you and your friends, then you can perhaps improve the quality of your web searches or share photos and so on and so forth. But I'm mostly going to focus on the first set, which is much more about using trust relationships. Well, I'm going to try to stay away from that word, trust, but using social relationships to try to improve security and reliability in internet applications. So the big question that I get asked from a lot of my colleagues who are more traditional sort of distributed systems folks is really, is this really going to work? People that think, for example, I was at Eurosys a few weeks ago, and some folks I was talking to, I said, well, what do you think about social networks? And their response was, yes, that's the thing that tells me what you're having for breakfast, and that allows me to throw sheep at my friends, right? So there's a lot of skepticism about how practical these kind of things are, and can they actually make a difference when it's about dollars and cents, and when it's, there's a real business involved. So the big question then is, are these things actually effective in practice, okay, or are they just good for poking around, right? And assuming that that answer is in the affirmative, then how do we build the right applications? How do we ensure that with some confidence that, from a technical standpoint, these applications are actually going to work? Right? So I'm going to try to answer these questions based on some of the measurement studies that my group have been working on. Now, this is mostly recent stuff from last year at SIGCOMM Workshop WSN and Eurosys this year. Okay. So I'm going to basically start with a brief, very short little measurement study about why social networks actually make a difference. Okay. Then I'm going to talk more about, the core of the talk is going to be on predicting performance of social applications using interaction models. Okay, and then I'll conclude. All right, so the first question is, are social networks actually usable? Right? Are they actually effective when you're talking about dollars and cents and the bottom line? Okay, what we are going to do is we're going to talk about this study that we performed on an online auction system. So this is kind of like eBay plus the social network. And this wasn't something that we actually planned on, but as we were looking at different, we're doing work on reputation systems at the time, and bounced into this funky site that had both. And we said, well, this is a perfect platform to sort of quantify the impact of social networking, to see if it actually is worth anything, right? So the highlight, or the one sentence sort of bottom line, is that yes, in fact, you can basically filter out some of the fraudulent attackers in the system. Now, it's not to say that it's going to extrapolate very well into other environments. That's yet to be seen. But this basically shows that there is some potential for actual good by social networks. So let me talk about that. So basically, we know that the online fraud problem is very much a significant problem. It's been that way for ages, and it's not really going away. Right? So if you look at reports, research reports, and if you look at media reports, online fraud and things like eBay is still $1 billion business, okay, year to year. And not only eBay, but things like even Craigslist, right? So one of the questions is, okay, well, can you actually use social links to try to limit some of this fraud, okay? Obviously, if you can show success, then this has a lot of implications on things like Facebook marketplaces, for example, that Facebook is trying to push as the next big thing, right? So how do you actually measure this? Turns out we bumped into the perfect measurement platform. There's this thing called Overstock.com. Essentially, it's a eBay-like site. They do auctions. It's a relatively small community. I think at least one order of magnitude smaller than eBay, if not two. But they have the social network. Essentially, people go online. They discuss items. You know, I really like this product. You like this product. We talk about the details, specs, whatever. And they actually form friendship relationships in a public forum. It's more or less like a public bulletin kind of thing. But then they become friends, and they associate, and they share messages and so on. So interestingly enough, if you go to their auction site, there's actually a How Am I Connected button that allows you to determine if you are connected in the social network to a particular seller of a particular item. Okay, so it's an interesting little feature. And before our study, I don't think they really tried to sell it as a big plus. For us, this was a great way to determine whether social networks were effective, okay, were useful. Because some people were on the network and some people were not. Okay, so here's the methodology. We got all the data about all their users. This was only about 400,000 users in their system. Not that much. It's a small population. So some of them belong to a social network, which essentially is this, as you might expect, a social network with friends. And some of them belong to a business network, which is essentially anyone that you've ever bought or sold something to. Okay? So once you have this graph, then the question is, okay, the big question, and I'll skip over the other things that we did in the study, the big question that we're interested in is, if you're in a social network, does it actually make a difference in terms of your satisfaction? When you buy stuff, are you more satisfied? Are you less cheated, right? So what we did was then we crawled a bunch of user ratings from the reputation system, feedback after the fact, after each transaction, and we want to see, maybe the social networking users are happier, okay? And we correspond this back to users who are either in or out of the social network. So here's a very simple picture of what the membership looks like. As you might expect, only a small percentage of the users, something like 12%, were on the social network. 80% were in the business network. In other words, they had bought or sold something. 80% were only on the business network. But what's somewhat amusing is that there's 8% of people who never bought or sold anything, but yet are in the social network. So they go on Overstock to chat about stuff, but they don't actually buy or sell stuff, which is a bit ironic. All right, so the key question, which I'll jump to, which is, does it make a difference? Okay, so we downloaded something like 18,000 transactions, and then we look at the feedback rating and match that back to the memberships of people involved. Okay, so how do we determine whether people were happy or not? Well, there's this feedback rating on Overstock, which is a very simple scale. It goes, unlike eBay, which is sort of binary, good or bad. Here it actually goes from +2 to -2, where +2 is great, -2 is I really got ripped off, as opposed to just a little bit. So for simplicity, we're going to say that anything +1 or +2 is a satisfied rating, and the rest are not. Okay, so just for simple calibration purposes, this is the simple rating satisfaction for users on the business network. In other words, if you're not on the social network, you're somewhere here. Okay, now the points, essentially, every point denotes a single user's transactions with other people of 2 hops, for example, or 3 hops. Okay, and it's an average satisfaction of those people, those transactions. Okay, so what this basically shows you is that, well, let me explain the count a little bit. So if you're on the business network, and if you had a transaction, right, we're mapping transaction feedback to the users, then presumably you're already connected by a single edge, right? Because that's what the business network does, is if you bought or sold something with person X, there's an edge formed between the two. So we had to at least remove one edge between the endpoints and then look at the remaining graph. Okay, so the first point here, that really represents users who have bought multiple times from the same person or transacted multiple times with the same person, because we've already removed one edge and yet they're still connected by a single edge. Okay, so as you might expect, repeat buyers are really happy. Otherwise, they probably wouldn't have gone back for repeat purchases. But what's interesting is that if you start wandering further away in the business network, your satisfaction goes way down. Okay, so presumably there's some artifact of these fraudulent users or cheaters on the edge of the business network that are actually doing a lot of cheating. Okay, and so that's what you see here. Now, the interesting thing is what happens when you look at the social side of things. So the same graph for users when both users are on the social graph, okay, social network. And the biggest thing is, of course, you know, if you're friends with someone, you're one hop away in the social network, clearly you're pretty happy in general, right? Otherwise, you've got a screwed up friendship. And in some senses, you know, you do see occasionally a few people who are not happy with their friends after the fact. But in general, you expect it to be 100%, and it is. But what's really surprising is that even if you go all the way out, right, you expect your friends to treat you well, but even your friends of friends of friends of friends of friends, 5 hops away, 6 hops away, you're still really happy with transactions. So this is what really took us sort of off guard, because we didn't expect this. We expected some sort of declining, perhaps slowly declining, but some decline. And in fact, this is, yeah, Alex?
So, you know, 6 degrees of Kevin Bacon,
Yeah.
right? 6 degrees should be basically everybody.
Exactly.
So what if maybe this just says that the fraudulent users don't actually participate in the forums, but doesn't actually say anything about the power of a social network. It's just when you're committing fraud, you don't want to put too much evidence out there.
Right.
So how do we separate the difference between what the social value of the network is getting us from the fact that criminals just try and...
So there's definitely an argument that you can make that says, you know, the attackers are essentially staying off of the social network because they don't want to be found, right? But the flip side of that same argument could be that if it's difficult to be on the social network and cheat, then in fact, if you expand the membership of the social network, presumably there'll be a challenge for the cheaters to continue cheating, right? Or the membership will be largely shifting towards the social network in the sense that they'll move to a safer community and be more protected, right? But I agree, it's not at all a conclusive argument that says, you know, if 100% of everybody on the site was included in the social network, would fraud still happen, right? Presumably, it still would, but it would take some other form, and there'd be other mechanisms to deal with. But I think this does show some non-insignificant proof that social networks can, at the very least, act as a filter to make it more difficult for fraudulent users to participate. Okay. So the quick conclusion that, yes?
So it seems to me that if you're trading with your friends, you're probably a little more likely to say they were great than they were strangers. So how do you deal with trust in the data set?
So we don't actually see this as a significant problem. Admittedly, you know, if you look at this particular point, it's really high. But there are people who rate their friends unsatisfactorily, right? So if you look at, if I can get my mouse, right? Some of these points down here, clearly some people are not happy with their friends. But I think the main takeaway here is not so much this data point, but the other data points. So for friends of friends, arguably, or friends of friends of friends, you have very little incentive to rate them positively because saying that they do bad things is not necessarily going to hurt you through the grapevine, right? So I think these are the important points that we're looking at out here, right? Yes?
What are the total number of transactions that you're seeing at the 4, 5, and 6 top level?
Right. So at that level, we're seeing about a few hundred to 1,000 transactions. It's pretty small in terms of numbers, right, relatively. But the trends are still pretty strong. In other words, there's a few stragglers at the lower levels, but really the concentration is still quite high. This is, yeah.
Do you have data for disconnected users? Users that are just disconnected from the social network completely, and what the satisfaction was for those users?
So the entire social network was fully connected in a single graph, and so there wasn't a notion of you belong to this social network and I belong to this one. So in those cases, presumably those two people would not be on the social network. If they were connected somehow. Yes.
What about a case where you have one person on the social network inviting someone from the social network, but obviously using the business network? What does that mean?
So that falls into this category. We're basically putting those data points in here. Yeah. So having one person be in the social network does not, we don't actually quantify, we don't separate out those transactions specifically. Yeah? Yes?
So it sounds like the way to echo Patrick, to test whether it is that people in the social network are just inherently more trustworthy, or whether the connection implies it, is to see whether the satisfaction differs when the seller is, or the buyer is in the social network versus not. on average, they're just more trustworthy by virtue of being part of the network.
Okay, you're saying that the less trustworthy people just will not join the social network.
Right. So it would be to, I guess, normalize the results using
Yeah.
the baseline trustworthiness.
Okay, so I think I get the gist of what you're saying, but I'm not quite sure. So the question is whether this is doable or not?
Yeah, or whether you have any kind of an indication of that.
So,
Whether people are, if you somehow isolate the fact that they're on a social network at all, there's some kind of
oh, I see. Look at the same identical population with or without the social. So no, we haven't looked at that. But in fact, I think even if you did look at that and it turned out a positive result, it will still reinforce the same conclusion, which is that, presumably the people who are joining the social network are the people who are not the cheaters, right? And that's, I think, our sort of message is that, from what we can understand, the reason why we don't have fraud on these social networks is because it takes a lot of work to actually join the social networks. And that's a lot of the basic idea behind these kind of applications is that it's essentially, if you will, a really high-level CAPTCHA. And it's not, you can't farm it out, you can't get other people to cheat it, there's no automated way to get around it, and that's how you filter out the bad guys, in a sense. Okay. So I don't mean to cut the question short, but really this isn't the point of the talk, so I don't want to spend too much time here. If we can save some of the other questions until later, I'd be happy to answer them. But otherwise, we're going to miss the bulk of the talk here. Okay, so anyway, so the message here is, okay, maybe it's worth something. Right? And now the question moves on to, okay, how do we build them? How do we evaluate them in an accurate way that is reflective of maybe, if they were widely adopted, what the performance would look like? So let me get on to this particular part. Right? So how do we evaluate some of these applications? And the simple answer right now is that people today are basically using either synthetic graphs or maybe social graphs that they crawled from things like Facebook or Orchid or whatever, and basically assuming, if we get really good adoption, then this graph is what the social connectivity graph is going to look like from our application. Okay, and if we run it in simulation, let's see how it goes. Okay. Now, the thing is that social scientists have a big problem with this sort of approach. Okay? Now, there's been a lot of history in social sciences and psychology that says, friends are not what they seem, right? So Stanley Milgram has, many years ago, back in the 70s, I believe, invented this term of familiar stranger, the idea that everybody has people in their lives that they know fairly well, by sight, by name, but they wouldn't necessarily consider friends. They wouldn't necessarily trade secrets with or even participate in a share key exchange or something of that sort. And then lately, there's been a lot of sociology work that coined the term of public displays of connections. This is kind of like PDAs, except PDCs. So the idea here is some people on Facebook, a lot of people on Facebook, especially undergraduates or younger, tend to collect friends as a status symbol, right? So I'm cool because I've got 2,000 friends and you've only got 200, right? So how do you separate these sort of artifacts from a realistic representation of which people will actually participate and make your application work? Right?
Another question.
Yes?
I didn't quite understand what you meant about collecting friends.
So for example,
How do you define a friend?
a friend is defined as, on Facebook, for example, you formed a social link between the two of you. Right? So I've added you on Facebook as one of my friends, therefore that ups my count of friends to X number plus 1. Right. So there's, in most of these social networks, there's a very explicit binary notion. You're a friend or you're not a friend. There's nothing gray, nothing in between. So getting a high count in a lot of cases means that you're very popular, right? You've got a lot of friends in some sense. Okay, so the hypothesis that we have here is that, if you do this wrong, if you sort of take a very simplistic, naive view of what the friendship graph looks like, this can actually impact how you design and evaluate your social applications. Right? So we're actually going to test this hypothesis out. So a few key questions, right? First of all, is the social graph a correct representation of what people are using Facebook for? Is it indicative of people's activity on Facebook, right? If they're not, what is the right way to capture interactions or active relationships between users? Okay? And then finally, does this actually matter, ultimately, to the people who are like us designing social networking applications? and hopefully deploying them. Okay, so the quick highlights are basically we try to answer all these questions using a Facebook study. Okay, Facebook is the largest, I think, today, social network, 200 plus million users. This was performed, most of this data was gathered in spring, early summer of 2008, back when Facebook only had about 66 million users. Today they've got 200 million plus, triple the size. So we downloaded about 10 million user profiles from Facebook. Back then it was a big deal. This was about 15% of all the users. We could have gotten more, but at some point we ran out of storage and we had enough data to play with. And it was sufficiently difficult to process that data as it was. Okay, so we analyzed not only the profiles and their connectivity, but also which users interacted with whom, how they interacted, by looking at application logs. Okay? And then based on this, we can basically say that a social graph, a naive social graph, is in fact far from representative of what people actually do on Facebook. And we go ahead and propose this notion of interaction graphs. Essentially, it's a smarter, more filtered subset of a social graph that you can apply different thresholds to. Okay? And basically what we then show is that if you, in fact, evaluate a social application using these two different models, the results are actually quite different. Okay, so it does make, in fact, it does make a big difference which model you use to evaluate your application. So we'll get to this in a second. All right, so how do we crawl this data? I think by now sufficient people have been using this technique that this is more or less public knowledge now. But basically, Facebook is organized into different networks. Okay, geographic or school or work. So the school or work networks often can be authenticated by email address or from pure introduction, but not the geographic ones. But by default, Facebook has this thing where if two people are on the same network, by default they can see each other's profile, which is a lot of information, right? So we essentially sort of use this fact to have a roaming user that sort of, if you will, think of a bot account that moves between different cities every day, right? In fact, Facebook does place limits on this, but once you get enough users in the system, it's not a problem, okay? So you jump to a particular region, say San Diego, get all the information you can, move on, right? And in fact, back in the day, this was a year ago, roughly about 80% of all Facebook users were a member of a regional network. And so the potential crawlable space was quite high. Yes?
How do you handle privacy settings?
So if the privacy settings precluded us from seeing the users, then we would get blocked when we try to retrieve that user. So roughly we got about 55% or 50% of all the users we could crawl. So we just use the data set that we could crawl. Right. There's some other minor details, but I'll skip over that now. Okay, so we crawled 22 of the largest regional networks, ranging from London to New York City to France, Turkey, et cetera. And in each case, we start with about 50 random seeds, and we've done sensitivity analysis to show that this is sufficient to basically get the really, really large bulk of all users in a particular regional network. The connectivity is really high, so even if you start with many, many more seeds, you only get a few more stragglers who are not connected to anyone else. So for each user, we get not only their profile, but we also get their application logs, including things like their wall posts, because wall posts are permanent. When you write on someone's wall, it's there more or less forever with a timestamp. And we also got their photo comments. In other words, a lot of people interact by posting photos, tagging other people, commenting on other people's photos. You can track all of these things with a timestamp. Okay, so we refer to these two log applications as interactions. These two applications are installed everywhere on every user, and by far the most popular applications on Facebook. Yes?
You take into account, you say this for the comments, you take into account tags?
Yes.
Okay, so because people are more likely to actually show up in the same place.
Exactly, yeah. If you tag someone, presumably if you were either the photo taker, or in the same photo with someone, that actually implies some level of physical proximity, which is more than you can say for most Facebook applications. Right, so some quick statistics about the data. About 10 million users, about 15% of the entire population. about 400 million social links. All the statistics look relatively similar to prior studies on ORCID. In fact, the power law coefficient is exactly the same, slightly lower error. Okay. Now, this was in 2008, so presumably a lot of this has changed. We know for a fact that the average degree last year was about 77 from our data. Now, according to Facebook, it's about 120. So connectivity has gone up significantly in a year. Presumably, some of these other characteristics also have. And we're in the process of verifying some of this data with new data right now. So the simple question is, the first question that we can ask is, how do you actually interact with your friends? Is it even? And intuitively, we know this is not true, right? Because a lot of people have, a lot of professional people who are very busy have a lot of friends, right? And in fact, I went ahead and looked at my entire friend list and tried to figure out who had the most number of friends. And it was actually Randy. I wonder if Randy's watching. Hopefully not. But so I didn't reveal any private information about Randy. But he has a lot of friends. And clearly this is a guy who is very prolific, very busy, does many, many things. So you know. That's right, exactly. And all their grandchildren and so on, right? That's quite a few hundred right there. So you know that he's doing real things. So in his very limited time, there's no way that he's interacting with 700 people. Okay? So the question really is, what does the skew look like? And so here's the first graph. Sorted by degree, CDF, number of nodes on the x-axis, sorted by degree, and looking at the total contribution of interactions across Facebook. You can see there's a good skew here. Yeah? Good question. So in this sense, we're simplifying things and we're saying undirected. If there's anything that happened in either direction between the two of you, then there's a connection there. Okay. Yeah.
That's a real graph.
Yes?
So perfect.
Well, yeah. When you look at 10 million users and 400 million links. No. I could show you all the dots, but they would just look more or less like this. So we made a thicker line to make it look prettier, but yeah, it's very smooth. Yes? So very good question. So we can't actually measure what we call latent interactions. These days, Facebook is much more about that kind of interaction. You update a status and many, many other people see it. They don't have to do anything. Those kind of things we can't track. Luckily enough, back in the day, or last year, before Facebook revamped their status, their whole format, you had to do more work to interact. And the whole Twitter-like interface wasn't in full effect yet. And so this is a bit more reflective. And you had less latent interactions in 2008. But very good question, yeah. So this is a real graph, and it is very skewed. And in fact, so, take a point. 10% of the most connected users are responsible for about 60% of all interactions. It's a bit high. But then if you sort users by how active they are instead of their social connectivity, this gets even worse. So about 10% account for about 85%. Okay? So
So where's Randy on this?
I have no idea. I don't dare check. Certain things I don't want to know. Right, so we were very careful to anonymize all this and not look into individual pieces of data. So then if you look at a cumulative fraction, this is kind of like a 3D CDF, if you will. You can see that for most people, for the half of the population who are the least skewed in their activity, 70% of the interaction comes from 7% of their friends, which is a very, very extreme skew. Okay? Another way to interpret this is that pretty much everyone's interactions can be attributed to about 50% or less of their own friends list. Okay? All right, so we know that this is skew. We know that the social graph is not necessarily very reflective. So the question is now, what do we do about it? All right? So we're going to produce or propose what we call interaction graphs. And this is very simple, drop-dead simple concept. Basically, the idea is you take a social graph and you filter out edges between users that don't interact or don't interact above to a certain level. So there's a threshold involved. Okay? And basically, you can set the threshold to your liking. Okay? And here's a picture that basically says that if you set the window of your interactions, and if you increase the number of count of interactions, you can quickly whittle down the number of edges inside the system. Okay? Yes? No. So we're not necessarily looking at filtering specific users out, because people aren't doing that with social graphs right now anyway, right? So what we're looking at is, how do you produce something that does mean something for the application developers?
Right. I guess my question is, by doing this sort of interaction thing, you're doing this on a pairwise basis. This is, have you and I talked in 4 months?
Mm-hmm.
Right. But I'm affecting your skew because, in other words, it seems like there are people in this graph who, if you actually wanted to extract anything meaningful from interaction, shouldn't be in the graph because they don't have any meaningful interactions. They joined Facebook once and went away.
Right.
And so it seems like if you were somehow, and I don't know how to do that pruning, but if you were able to do that pruning, presumably, because like you said, those skews are very extreme.
Yeah.
And I just wonder if that's an artifact of Deadwood.
I think it's more general than that, because even if you trim off the really inactive people, the trend is very much, is like you said, very strong and very pervasive. So it's not clear that eliminating some sample users will fix that problem. In fact, I'll show you the next slide, in fact, what happens when you do try to prune those users out. So in a sense, we did do something, but more as a side effect of something else we were looking at. So the idea here is that you can prune different levels of interactions out, and you can produce ever more indicators, social graphs that are more active and more active. And these graphs are tunable in a sense. So the simple question that we look at is, first question we look at is, what does this graph look like? Okay, what does the degrees look like on here? And you compare it to the social graph. Yes?
You kind of normalize based on the activity of the user itself. So I may not be terribly active, but I do talk to my friends once a month. But you would have to prune me because someone over here was talking to everybody 3 times a day.
No. So we're looking at a basic threshold. So once you pass that basic threshold, you belong in the set. In fact, for most of our graphs that we're going to show here, we're using the most general. In other words, if you interacted with someone ever, even once, ever since you joined Facebook, you're on this graph. So this.
You're dropping the links though, right? You're not actually dropping the nodes.
Right. Well, we will drop nodes if this person has logged on, has never done anything with anyone ever. So they become a single dot.
Basically, you prune the links and you prune those that have the degrees to it.
Exactly. Yes, exactly. So then you look at this graph, this resulting interaction graph. Again, this is the most conservative possible graph, right? If you wrote one message between the two of you in the 2 years that Facebook has been around, or whenever you've started your account, you're on this graph. Okay. So the red line is the 45-degree line, right? If the interaction degree matched your social degree, that's where the line would be. So clearly, it's nowhere near that. And in fact, it's interesting because we know from sociology and communications that there's this Dunbar's number. Robin Dunbar in the UK had this social theory that everyone's critical, your brain power is limited. There's only so many friends you can keep track of in any meaningful fashion. And that magic number is supposedly around 150, right? So in fact, that's where that number is. Now, one of the first questions that people asked was, well, it looks like some of your friends are actually exceeding that number. That's, superpower humans or whatever. But in fact, if you look at 99th percentile of all the Facebook users are actually below that number, significantly below that number, in fact. Okay, so this is actually consistent with social science results, and in fact, again, if you recall that this is a very conservative view of the interaction graph. This is if you've ever talked to this person in 2 years or whatever. Okay, so these are all good, and now the question is, what does the actual graph structure look like? Does it actually change significantly? So you look at the social graph, which is 10 million users when we started. Excuse me. And you ended up with 8.4 million users. So something like 2.2 million users did absolutely nothing with anyone. So they're gone, right? But interestingly enough, what's interesting is that the number of edges went down by a lot, by a factor of 4. Okay, even though the number of users only went down by something like 20%. So clearly, the graph has gotten a lot sparser. All right, and if you look at the statistics, it's in fact true. The radius, diameter have all increased. Average path lengths increased a lot. Clustering coefficient has gone down by a factor 2, which really tells you that the sort of interconnections between nearby friends is much, much lower, right? Still power law, in fact, same coefficient, but the error is in fact much lower. So that nasty tail towards the end of that power law fitting has now been thinned out quite a bit. So, this is all good, but then the next question is sort of, does this actually mean anything? right? So we've now produced a hopefully more accurate model, hopefully more believable and more indicative model, but now does it actually make a difference when you try to evaluate social applications using these two different models? And that's what we're going to do. We're basically going to look at two of these fairly popular applications, Sybilguard from SIGCOMM 2007 and Reliable Email from NSTI 06. And basically, these two applications do very different things. And we're going to try to see if evaluating them differently will make a real impact on the results. Okay, so quickly now, I'm going to talk about Sybilguard just as background to explain what Sybilguard does. Sybilguard basically uses social graphs to weed out Sybil accounts. Sybil accounts happen when, for example, a single user gets many, many identities online and uses them all to collaborate in some way. You can fool reputation systems, like in things like Overstock, or you can use them to collude and do things like play around as a gang in things like mob wars. So some colleagues of mine and I actually wrote a paper in 2007 that actually measured file sharing systems and showed that there were, in fact, real Sybil attacks occurring on the internet. And so this is not sort of an imaginary artifact. And basically, the high level, I'm going to try to go through this fairly quickly, is that this is what happens. So let's say that you have a social graph, right? Sybilguard says you're going to exchange some keys with your friends, fairly low computation, symmetric keys. And then basically, let's say that A wants to verify if B is a real user or a Sybil identity, okay? What it's going to do is A and B both send out these, what they call deterministic random walks. I won't get into details, but basically they're more or less random walks towards the graph. And you're going to look at where they intersect. If there are many intersection points, then that probably means that it's a normal identity. It's a normal user. Okay, and A is going to get this information back, and there's an algorithm for determining and guessing whether this is a good person or a Sybil. Now here's a counterexample. The idea is if I've got a bunch of Sybil accounts, it's going to be very challenging for me to connect all of them to real users, right? So the connection point between them, presumably they're connected themselves, to the rest of the population is going to be a fairly concentrated number of nodes. Okay, yes?
Why is that necessarily the case? It's difficult to connect them to?
Because let's say I create 1,000 Sybil accounts, right? Now, how much time do I have to take to socialize before I can connect 1,000 of these users to, say, 1,000 normal users? Highly unlikely, right? Yes, but if you're talking about Facebook, for example, it's going to be much more difficult, right? You can make random requests, but most likely people are not going to respond, especially if you've got some randomly generated.
People don't add friends that they haven't met in real life.
Right, so that's the model that you want to work, right? Clearly, Facebook necessarily doesn't conform to that model, but we're going to use the interaction graph, and hopefully that fits that model. These are at each other. Oops, sorry, did I touch something? Okay, so then the assumption is that this intersection point in the middle is going to be crucial. So you do this random walk, and in fact, they're going to intersect mostly at a very small number of sites between the prober and the suspect, okay? So that's how you detect potentially Sybil identities. And, right, so the big thing here is that Sybilguard requires a lot of trust, requires real interaction, requires you to actually share a key with one of your friends. Now, whether we can talk about trust or not, but if you don't, even if you trust someone, if you don't interact with them on Facebook ever, you're probably unlikely to share a key with them, even if they're your sister or your brother, okay? So then what we're going to do is we're going to see, okay, what happens if you use interaction graphs to evaluate Sybilguard instead of, say, the social graph? Okay. So what's the worst case scenario for Sybilguard? Worst case scenario for Sybilguard is that you don't actually get a result back. You do a random walk and it can come back and loop upon itself, and you get a self loop. In this case, the random walk becomes completely useless, okay? And you don't get any sort of indication, positive or negative, about the attacker or a potential attacker. So here's a result, right? So if you make random walks really, really long, turns out that you can get fairly good intersection rate, which means all your probing walks out there will get you some information back, okay? But it turns out if you use the interaction graph, that number drops. So now you have something like 9-10% of users who, or sorry, 9-10% of random walks who are just not returning. They're giving you no information. And it turns out if you look at a more precise or a more higher threshold intersection graph, right? If users actually talk to each other, if users only share keys because they interact on a fairly frequent basis, once every 2 months, let's say, then this graph is even sparser. And in fact, something like 30% of your random walks get you nothing back, which is fairly disappointing. Yes?
Is the graph still contiguous?
Oh, yes. For the most part, yes. Yes. There are partitions that fall off, but we're ignoring those partitions for now. We're looking at the weakly connected component. So this is sort of surprising. We didn't quite expect this. We thought performance would go down a little bit, but 30% is a fairly sizable number. Now, it's not all bad. So some applications can actually benefit, right? So reliable email is a very simple idea that you only whitelist mail that's from a friend or a friend of a friend. Okay, now, what happens? Well, now we're trying to evaluate this, and we're saying, okay, what's the way to evaluate RE? You can imagine that if you compromise a social account's user, a social networking account, then you can use that account to go ahead and spam people reliably using this whitelist network, right? And these days, there are in fact a lot of phishing attacks for Facebook and social network accounts out there. That's a big new vector of attack. So that's what we look at. We look at and say, if X number of users get compromised, what is the damage? What is the level of damage that can be done by RE? Okay. And it turns out that, in fact, using using the interaction graph gets you better results. Because the graph is sparser, it means necessarily that you're going to have less reachability. And in fact, your spam is going to go to less people. Right? So arguably, this is hopefully a more accurate version of who you would actually trust to get email from. Right? So you would presumably whitelist less email accounts, and that is why potential spam, in fact, can be further limited.
This graph looks like the percentage of receiving spams actually decreasing.
That's right. Yeah.
What is the
So the interaction graph is the bottom 3 lines. That basically says if you evaluate this using interaction graph, what?
You just look at the social graph line for large fractions.
Oh, all the way out there, yeah. Right. So there's an explanation to this. Basically, the very minuscule drop-in effect is the fact that when you take users out and you say they've been compromised, in fact, that reduces the possible set of spammers. That reduces the possible set of recipients for spam email. So that actually drops your 100% reachable population. That's why that line goes down by a little bit.
So this result's great, and it's, I guess, fairly expected now that you've walked us up to it. But from the point of view of RE, this is only half the problem, right? Because we still have the false negative issue, which is, am I actually going to be able to send mail to anybody? You know, if I can only send mail to the people I talked to yesterday, it's not a really useful system.
Exactly. And you might as well just use Facebook messaging or something like that to that effect. Right. So, yeah, we're not necessarily saying that, these applications are fantastic, just that from what we've seen, in fact, it does make a significant difference.
So I guess my question is, have you tried I forget how the RE paper evaluated their false positive, false negative, but did you redo that experiment as well? And does the delivery rate hold up?
No, I think we actually tried, and it turns out I don't think we have sufficient data to simulate that experiment to any degree of accuracy. Yeah.
Were there any significant differences in runtime of actually doing the computation across these graphs? If they're smaller or the graphs just not that big for the data sets?
Well, in either case, in fact, it took a lot of time. Particularly Sybilguard simulations usually took hours, sometimes close to a day, depending on the size of the graph. But yeah, if the graph was sparser, much faster. So yeah, there's a sort of additional benefit, yeah.
This is a number of people receiving any spam. What's the reduction in total spam?
That number I actually don't have for you. We have that in the log somewhere, but I can dig that up. We didn't actually look at that. We only looked at sort of the full reach, the reachability of the spam, not necessarily the distribution or the total count.
Are you able to distribute if
Sorry, I didn't catch the end of
Are
it.
you able to attribute why you were receiving spam when someone was not your friend, but like trace the friend to have the friend?
No, at least not from what we have right now. You still have a lot of friends of friends, and it's very difficult to track back without some external mechanism to mark it. Yeah. Any other? Yes.
So, what if you were to take, I don't know if you have an answer to this, but what if you were to take the original full social graph and delete edges at random until you have the same number of edges as the interaction graph? Would that be, in other words, what I'm asking is it just because you have fewer edges, or is there something more?
Right. So, very good question. We haven't tested that out. We're, in fact, in the process of evaluating that right now. Very, very interesting question, yeah. Okay, so, actually finished a little bit ahead of time. So the conclusion basically is fairly straightforward. One, I think we've hopefully shown that social networks can, in certain aspects, actually make a positive impact on real applications. Right? So that was our sort of motivating factor going forward. And then 2 and 3, hopefully showing that basically traditional social networking graphs are not the right model for evaluating social networking applications. And this interaction graph stuff potentially could be a more accurate representation of user activity and hopefully then be a more accurate representation of what people will actually do once they deploy the application. And yeah, some citation, then we've got this data set available, so if people are interested, they can talk to me about that, yes.
Going back to Sybilguard, we often hear the pattern where one node is judging between 2 subnetworks, which are not otherwise very well connected. So we often hear that these are naturally occurring topologies in organizations because people are central facilitators and so on. So we usually think of it as a very good thing. And now you call them names. So.
Right. Well, that's hard to say. So what we can show you is that this does make, in fact, actually, yeah, so at least from our perspective, this isn't necessarily a good thing. Okay, we're only looking at the perspective of actually deploying these applications and running and seeing what they do.
So I guess if you could put that in form of question, have you checked if those are Sybil's or naturally occurring topologies?
That we can't actually determine. It's very difficult to actually trace back to see if these are fraudulent users versus naturally occurring users as part of the graph topology. Yeah, but we'll try. Yeah, the users. Okay.
So I want to return to the overstock graph if we have time, because this is such a sort of seemingly compelling story, but I'm just trying to understand what's going on. So in that one graph, the reliability went to zero, not the reliability, the satisfaction went to 0, right, which is just striking.
Yeah.
One would expect that you'd have sort of a steady degradation. So did you look at that data to sort of understand, was it like one fraudster that was connected on a string? I mean, how does that happen?
So,
because you've got to connect to somebody close to 5 hops, right?
well, it's a very interesting question. So we can discuss this offline. My theory is that the attackers never get a second transaction from the people that they cheat. And so in some ways, they're, if you will, stuck at the outer rims of the business network. And they basically get very few interactions with meaningful users who are, for example, in the core. That's sort of my theory. It's been difficult to actually verify that with any confidence. And since all the data that we have is highly anonymized, we can't actually trace back to individual users and see their individual history. We can only look at a limited set of transactions. But yeah, that's sort of my very guesstimate kind of explanation. But it is a very striking result, artifact. And one of the things that we're looking at right now is, in fact, revisiting the same data and looking at changes at Overstock since it's grown significantly back then, since 2008. We're trying to verify some of the results that we've had previously. Okay. Did I get them all? Great. Thanks.